Hello everyone, welcome back to the channel Master the Codes, and today we are taking the fourth part of the graph series tutorial, and the topic for today is the depth first search, that is DFS. And in this series is for all those preparing for placements or coding interviews, or who have just started learning DSA and want to gain more experience in it. So to keep the channel flowing and the content growing, please like, share and subscribe to the channel and hit the bell icon for more such notifications and related content. So without wasting time, let us get started. In the previous part we had talked about depth first search. In the rather we talked about breadth first search, and today we are going to talk about depth first search. Right. It is also a part of a traversal, like you are given a graph or you are given a tree and you want to explore it or see what it all looks like. So it is for this. This depth first search technique can be used in multiple data structures like trees, matrix, and graphs. All of them which are non-linear data structures. Right? So, and in the previous videos, like I have told you, depth first search uses a data structure termed as stack. And if you don't want to use stack, you can directly use recursion as well. Preferably in most of the interview questions, they prefer you do the questions using recursion rather than using stack. I'll tell you both the approaches, but for in this particular video we are talking about only recursion because it is most, you can say, drifted towards coding interviews and other stuffs. So let me create a graph first and then I will explain you what all things are required. You can say there is a graph like this. If I would be going BFS, which you have seen in the previous video, and for all those who have not watched the previous video, go to the third video of the graph series and there you can find it, all the details about BFS. And for all those who are new to the channel, please like, share, subscribe. Right? So if this is your source node, and you are using BFS, what will happen? You will first go to the neighbor node 2, then you will go to the neighbor of node 3 and node 4 simultaneously. Then you will go to the neighbor node 6 and then you will node 5, and then you will go to node 6. But if you are using DFS, if you go to node 2 and supposedly you go to node 4, then you will not go to node 3 unless and until you have not explored the entire branch, such that DFS goes branch wise. It will explore one branch at a time, and then it will go to the next branch after it has completely explored. Right? So first it will explore 4, 5 and 6. Now there is one issue in DFS, like you have one branch like this and you have another branch, let's say like this, and you supposedly start from node 2 and you are going this way. Then you will go to node 3, you will go to node 4, you will go to node 5 and you will go to node 3 again. And the DFS may get stuck in a cycle. Right? This can happen, like in a graph there can be cycles. The most prominent difference between a tree and a graph is that tree does not contain any cycle, whereas graph may contain cycles. It may contain. It is not guaranteed that it will, but it may contain cycles. Right. So to solve this issue, to solve this particular issue, we use a visited array, like we same used in the BFS. Right. So this is a basic intuition of depth first search. Like it will explore the one branch at a time, and it will explore that particular branch entirely, and then it will slowly backtrack and explore the other branches in the graph or a tree given. Since here we are talking about graph, so we are dealing with graphs. Right. Now what is the algorithm? The very first thing, we need to create a visited array, and we enter the source node into the stack. Now if you are using a stack, you can directly use recursion. I will explain it to you with an example, but first let us see the algorithm. And then we check a neighbor of the node, right? Add it into the stack and mark as visited. This is the main thing which I wanted to say. Mark the node as visited so that it doesn't get stuck in a cycle. And when all the neighbors are visited, we backtrack, right? We recall, or rather we use the recursion technique and repeat it till the stack becomes empty. And when the entire recursion becomes empty or the stack becomes empty, the algorithm ends. Now let's take an example to make things a bit more clear. Assume you have node 1, then 2, then 3, then 4, and you have 5, 6 is then connected to 7, then 8, and then 9. Right. And yeah, that's the graph which you can see. It is a bit complicated, and you can assume we have this as the source node or our starting point, and we are using DFS. Now a general algorithm of DFS, I'll write it down, but first let us create the adjacency list or the mapping. So for all those who have not watched the adjacency list or who don't know what is adjacency list, go to the first video in my graph series. There you can find what is an adjacency list. Since it was always required in a graph, you need to convert a graph into adjacency list to solve it. So if you look over here, node 1 is connected to 2 and 5. Node 2 is connected to 1, 6 and 3. Node 3 is connected to node 4 and node 2. Node 5 is connected to 1 and 6. 4 is connected to 3. 6 is connected to 2, 5, 7 and 8. 7 is connected to 6. 8 is connected to 6 and 9, and 9 is connected to 8. This is what we call an adjacency list which we have prepared for our graph. Right. Now what all I need to do? First let's jump on to the function which we need to use or which we want to have. The function states that I have a function and it will have 3 parameters, or you can say 3 parameters. First would be the adjacency list, the node, not source, rather the current node, and the visited array. In this function I will run a for loop for where I will get each neighbor of current node. Okay, and for that each neighbor I will run or recursively call this function again over the adjacency list, and here the current will be changed with neighbor, and the visited array will be remain as same. The visited array will remain same, and in the beginning itself we will mark the visited of current as true. Right, I will explain you the code. I have created the code timestamps as well. This is just the basic recursive function which we are going to use for our DFS. Now coming to the algorithm, the first thing is we need to create a stack. Okay, now what I will do, create a visited array. I will create an array that is of 9 nodes and mark them currently as false. 5, 6, 7, 8 and 9. Then I have a stack. I will put the source node into it. Right, then what I will do, I will explore one of the branch. Let's say the branch is 2. Right, and I'll mark it as visited. Okay, the branch is 2. Now I am adding 2 into it. Then it will explore the next branch, that is from 2 it will go to 3. It will be in the same branching tree, but it will just jump onto the next nodes, or it will move to the next depth. Right, and I will mark 3 as visited. Then in the stack from 3 I will add 4, which is the last node or the leaf node. Right, this is what you call as the leaf node. The uniqueness of leaf node is that it has only one edge. That is what you call the leaf node. Now since I have marked 3 as visited, look at this, line number 5. When all the nodes are visited, right, all the neighbors are visited, we backtrack. So we will remove 4, and I will mark 4 as well, and 4 will be marked here as 2 was already marked here. Right, so if I look over here, 1 2 3 4 5 6 7 8 9, currently 1 is marked, 2 is marked, 3 is marked, and 4 is also marked. And since 4 has neighbor only 3, and since that neighbor is marked, I will backtrack. Then I will look for 3. Since 3 has 2 neighbors, that is 2 and 4, this one and this one, and they both are marked, I will remove 3. I will go to 2. Now the next neighbor of 2 that is not marked is 6. Right, this one, it is not marked because 1 is marked already and 3 is also marked already. So we will mark 6 and add it into the stack. Now from 6, take a neighbor of 6 which is not marked. 2 is already marked, so let's take 5. Right, now 5 is marked. I will mark 5 as well. And then I will check if this 5 has any other neighbors that are not marked. 5 has neighbors 1 and 6 that are already marked, so I will remove 5. Now I'll get back to 6 again and check if 6 has any other neighbors which are not marked. I have a neighbor of 7. Right, 7 is not yet marked. I'll mark 7. Then I'll add it into the stack. And since 7 has all the neighbors that are marked, I'll remove it because 7 is also a leaf node. It also has only one edge, and that edge connects to 6 and 6 is already marked. Now from 6 the only node that is left which is not marked is 8. And 8, now we are here. Now from, we'll mark 8 as well first. Now from 8, if there is any neighbor of 8 that is not yet marked or visited, that is 9. I'll mark 9 and add 9 into the stack. And since 9 is also a leaf node and has only one edge that is marked, I'll remove 9. Right, the stack now becomes 1, 2, 6 and 8. And since 8 is already marked and all the neighbors of 8 are also marked, that is 6 and 9, I'll remove 8. And 6 has neighbors 2, 5, 7, 8 and 9. 2, 5, 7, 8, 9, they are all marked, so I'll remove 6. Then I'm left with 2. 2 has neighbors 1, 6, 3, they are all marked, I'll remove 2. I have only node 1 and it has neighbors 2 and 5 which are all marked. I'll remove 1 and the stack now becomes empty. And when the stack becomes empty, the algorithm ends. This algorithm takes order of n time and order of n space if you are using a stack, and order of stack space if you are using recursion. They both are almost the same, right? They are same, you don't need to worry whether it be n square or n. It would probably be almost equal to n, so you can write it order of n as well. So that is how DFS works, right? It uses the LeafO concept, last in first out, and pops element from the back. Now coming to the applications where it can be used, like similar to BFS, it can be used to count the number of nodes, and it can be used to count the maximum depth of the graph, right? As if I take an example like this, clearly you can see the maximum length of graph is 3 over here, or not 3, you can say 4 because there are 4 nodes from 1, 2, 3 and 4. So this gives the maximum depth as 4. For this you can use it to find the number of paths. See, whenever there is this pop operation, we are going to a new path. Right, so if you look at it, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 various paths. Like one path can be this, one path can be this, one path can only end at 2, so there are 9 paths in all. So that is a way by which you can use to count the number of paths, again using greedy calculations, and the most important is to detect cycles. Now let me clarify one thing. given a graph like this, and assume you are given a graph like this, right? This entire thing is termed as a cycle, and this is termed as a loop or a self loop. In a cycle, there must be greater than one nodes, always. Like the smallest cycle that you can have is of node 2 nodes. That can be the smallest cycle. But in looping, there is only exactly one node. So that is how you differentiate between a loop and a cycle. Now, this DFS is used for cycle detection. And remember one thing, we never use BFS for cycle detection. The reason, I'll explain it in the next video, because for that I would first have to explain the cycle detection algorithm using DFS, and then I'll explain you in the next video. Since next video mostly is for cycle detection algorithm itself, so at that point of time I will explain you why we prefer DFS over BFS. DFS is better than BFS in cycle detection, right? So now we will move on to the coding part, where I will explain you how you need to implement it. Just a small detail I would like to give for all those who don't know what is recursion. I will make a separate video soon and explain you how to do it, like how does it work with the entire call stack and everything. So until then, you can just watch and have a look at the video, and I will make it a video within a day or two and will post the link in the description down below. Also, please like, share and subscribe to the channel for more notifications, right? And now we are gonna jump on to the implementation part of DFS algorithm. Like here is the input class. Again, similarly we are taking the number of nodes and the number of edges and n. This data will always be given to you if you are solving a graph question. Now we are defining the graph using the map of integer type, and the values are list of integers, creating an adjacency list. If you don't know why we did and how we did it, please check back to my first video of the graph based tutorial. I have explained everything in there. And now we'll fill the edges. So the reason I use this split is because I am giving input like this. Like 1 is an edge of 2, and in between I am giving a space. So to understand this type of input format, I am using this particular technique, taking the input and storing it into an array. Like at 0th position it will be 1, and at 1st position it will be 2. Similarly at 0th position it will be 5, and first position it will be 6. And adding them into the adjacency list. And then I'm calling this DFS algorithm, where you can say your parameters are the adjacency list, the source node, number of nodes. They are not even required, so I can simply remove them. Number of nodes and the visited array. Now I have taken the visited array of size n plus 1 because the nodes are starting from 1 and the indexing is starting from 0. So to take the nth node into consideration, I am giving one extra size. Now similarly, as in the pseudocode I have explained, mark the current node as visited, right? And I'm just printing it. every neighbor, right? Now I'm taking one branch. Out of all the given branches, I'm taking one specific branch and checking if that branch is not visited yet. And then if it is not visited, I'm applying DSS for it. Recursive. This is a recursive call. Right. Now the main thing which you can note over here is this. I'm using source node over here, and here it is changed to neighbor. Right. If I am currently at node 1, my neighbor is node 5 for this particular function. But for this particular function, my node will become 5 and neighbor will become 6. So that is how this recursive call is. And when there is no neighbor that is not visited, like all the neighbors are visited, suppose over here, then it will backtrack to 8 and then to 6 and then to 5 and then to 1 again. I've explained all the entire logic in the few minutes before. So there you can have a look. And that is how you write the code for DFS. It is a recursive call, so it is a quite small code as compared to DFS, where you have to maintain a queue and you have to write it down separately using dot is empty and extracting every node time and time. So it is a small as compared to that. But it is a bit complex. For that, you should know how to use recursion. Then only can be able to write. I'll create a separate video for recursion as well. Now, if you take this particular graph as we have drawn into consideration, let me take this input, right? Copy it and paste. So here's the output which we are getting. First, I'm going to node 1, then I'm going to node 2, then 3 and node 4. So first I'm exploring this particular branch. Then I'm going to node 6, right? And from 6 I'm going to node 5, then 7. And then I'm exploring this particular branch, 8, 9. So, and when all these nodes are explored, we backtrack back to node 1 again and end our recursive call. So that is all from my side for today. Everyone, please like, share, subscribe this channel. I provide this code and the note and the video link for other videos or the playlist in the description down below. So please make sure to hit the bell icon for more such notifications. Since this types of videos will be quite helpful for you, especially for placement, interviews, and for any other coding assessment.